Hello and welcome. Today we're going to take a look at a new Leetcode problem, Leetcode 98, validate binary search tree. Given the root of a binary tree, determine if it is a valid binary search tree or BST. A valid BST is defined as follows. The left subtree of a node contains only nodes with keys less than the node's key, and the right subtree of a node contains only nodes with keys greater than the node's key. Both the left and right subtrees must also be binary search trees. And we're given here two examples. So for the first example, we can see that we have nodes 2, 1, and 3. And if we go left from the root to node 1, we have a BST defined by just node 1. So that's a binary search tree. And 1 is also less than 2, so that's also valid. So the left subtree is valid. And then the right subtree is also valid because 3 is greater than 2, and it's the only node in the subtree. So this is a valid BST. And in example 2, we have here 5, 1, 4, 3, 6. And we have node 4, which is to the right of node 5. And it's less than 5. And this is wrong. This is not valid. This is not a valid BST. So we have to return false in this case. Right, so let's go to the drawing. So how do we approach this problem? Well, we need to somehow set some thresholds, right? When we compare the minimum and maximum values that are valid for a particular binary search tree. So if we start with the root node 2 for the first example, we have here 2, and we can use a min and max by default. So this is going to be equal to min and max int. Min and max int. And obviously 2 is between min and max, so that's a valid condition. And now we go down the left subtree and we check 1 between the updated limits. We have updated limit, so we're going to say min. But then we're going to say 2 instead of max, right? Because 2 was the parent, and 1 cannot be greater than 2, and it isn't. So we go, there's no other children here, so we just go, there are no other children, so we just go back and return true. And then on the right side, we have element 3. And we have 2 as the minimum, and then max. And now again, 3 is between 2 and max, right? So that's also valid, so we also return true from this branch. So we have here a valid BST. Valid BST. Right, so that was the first example. Let's go to the second example. Again, we set our limits as min and max initially, so min and max int. So 5, min, max. And on the left side we have 1, min, 5. So this will go back up with true. And on the right side we will have 4 with minimum 5 and max of max int. So we can see here that 4 is not between 5 and max int. So this will evaluate to false. Right, so then we return false here because this is an invalid BST. Invalid BST. Okay, so that's how our algorithm will work. We just use the min-max limits and we update them to the current node each time we go down on the left or the right branches, and then we always check that the current node is in between those two limits, the current limits. And one more thing, if we have no children, or if the node itself becomes null, then we just return true, because that's a valid BST. That would be the base case. So let's go and code this. Okay, so we're going to use a helper function. So we need because we need our min and max values to be passed around. So I'm going to say return is valid BST helper numeric limit int min numeric limits and max. Now we just have to define this function. Tree node, we take in a node, and we take in the min and the max values. Okay, so we said that if we have a null node, we just return true. Okay, if our node value is less or equal to min, or our node value is greater or equal to max, we return false, right? Because then we're not in a valid BST. And otherwise we return true. But we also need to check the subtrees, right? We need to check the children of this node. So if we recursively check if node left min and the current node value, so we bound the right side with the current node value, sorry, the left side, but the maximum will be the current node value, then we return false. And if on the right side the minimum is not between the current node value and the maximum, we also return false. Okay, so I think this should cover it. Let's see. Yes, the two cases were accepted, so let's submit this. Oh, wrong answer. This looks like max int, so I'm going to change this to something like long, just to be sure that we have enough precision here. Long, and let's submit. Okay, 100%. So in terms of time complexity and space complexity, we'll have ON, because we visit all nodes, and space complexity is going to be also ON due to the recursive stack. Okay, we can also see this if we analyze complexity here in Leetcode, and it's ON. Okay, time complexity. Okay, thank you for listening. I hope you enjoyed the explanation. I hope it was helpful. If it was, please like and subscribe, and stay tuned for more C++ problems. Thank you and bye.